Welcome my friends, welcome to my next lecture. Now if you recall, in my last lecture I was talking about the functions of bounded variation, and then my plan for today's lecture is to introduce or to recall the definitions of Riemann Stietjes integral. Now once I have that one, then I can define what do I mean by line integral or contour integrations, and then I'll talk about path independency and then Cauchy-Goussat theorem. Okay, so maybe I think I should start with or I should recall the definitions of Riemann Stietjes integral first, okay, very briefly, and then I'll go to the definitions of contour integral and more on the contour integral or line integral. Okay, so as I said, I just recall the definitions of Riemann Stietjes integral. Now in my last lecture I was talking about, well, what is Riemann Stietjes, what is Riemann integration. So you know the meaning of these integrations a to b fx dx, and if you just recall what is the definition is that, so if I have an interval a to b, then first you have to have a partitions, right? With respect to that partitions, you can form a Riemann sum. Suppose this is my partition, say x naught, suppose this is xn, and suppose this is xi minus 1, this is xi, so this is xi minus 1, this is xi. Okay, if I have this one, so x naught, x1 up to xi minus 1, xi up to xn minus 1 xn, then corresponding to that partitions I already discussed, you should make what is called Riemann sum. That means in sum over I from 1 up to n, f of xi I, then the length of the interval, subinterval xi minus 1 to xi. Okay, and what is xi? Xi is some point inside the interval xi minus 1 to xi, and one can prove that if limit of the norm of the partition goes to 0, then this what is called Riemann sum, that this limit exists and it will give you one real number, and that you can think about as a Riemann integrations of f with respect to or the Riemann integral with respect to dx. Okay, so now the same notions I can extend in the context of what is called functions of bounded variations. What does it mean? Now I am saying that I will give the same definitions that you know in case of Riemann integration. So Riemann Stietjes integral is nothing but I am talking about the integrations of f. Now this time I am talking the integrations of f with respect to a functions of bounded variation. That means I will give a meaning of integrations f x d nu x. This is actually functions of bounded variation. Okay. Now if take nu x is equal to x, then it will give you what is called Riemann integrations. Okay, so that means what sort of definition I will give? Same definitions. So I will have a function, say f nice functions, very nice functions. Suppose it is continuous functions. Assume that I have a functions of bounded variations. Then I will take a partitions. I will take a Riemann sums, and I will say that okay, if norm of the partition goes to 0, when that limit will exist, and if the limit will exist, then I will say that this is nothing but the integrations of f with respect to my functions of bounded variation, and that I will say that Riemann Stietjes integral. Okay, so this is the same. So it is just the parallel extensions of Riemann integral, but this time I am integrating with respect to a functions of bounded variations. Okay, so let f is a map from closed interval a b to c be a continuous functions. Suppose you have a functions alpha from a to b c, it's a functions of bounded variations I already discussed in my last lecture. Now you consider a partitions p from a to b whose a is equal to x naught, x1 up to xn is equal to b. I am considering any point xi or ti inside the interval xi minus 1 to xi. Then I am forming a Riemann Stietjes sum, which I am saying that it is depends on my partitions p and my functions of bounded variations alpha. Of course it should depends on my functions f, so therefore I am saying that this is spf alpha, which is nothing but just the mimic the kind of corresponding Riemann sum that you are comfortable in real analysis, that you have the functions of value of my functions at some point in the interval xi minus 1 to xi, that will be there. Now earlier you will have xi to xi minus 1, that means the length of the interval, because my function was alpha of x is equal to x. Now this times I have a functions alpha, arbitrary functions alpha. So what I am doing, this should be alpha of xi minus alpha of xi minus 1. Okay, so now you can see the parallel. So earlier you will have xi minus 1, and why is that? Because this time I will have alpha x is equal to x. That is why it boils down to this one. So this time I am given a function shape, given a functions of bounded variation, given a partitions p, then I will have this sum spf comma alpha, which is nothing but the value of the functions at some point ti is some point xi minus 1 to xi, times alpha of xi minus alpha of xi minus 1. So this is the corresponding Riemann sums. Now then I am saying that, okay, well, if there exists a number I such that if norm of the partition goes to 0, if my Riemann sum converges, where norm of the partition means maximum of the length of the interval Ti, okay, this should not Ti minus 1, this is actually, I should say, xi minus 1. So this is a typo, no, not Ti. Ti is the in-between point. So it is the length of the interval. So you take the length of the interval xi to xi minus 1, take the maximum, and this is, I am saying, the norm of the partitions. Okay. So now if norm of the partition goes to 0 and if the limit I exists, then I will say that, of course, there is a catch actually. It says that this limit should be independently of choice of the points, because if I change the point Ti, then corresponding Riemann sum will change. Okay. So but whenever I will say the norm of the partition goes to 0, limit exists, that means it should be independent of the choice of points Ti. Then I will say that my function is Riemann Stietjes integral with respect to alpha, and I will denote it by I is equal to a to b f d alpha. Okay. So in the case of Riemann integration, same thing. If I form a Riemann sum where xi I is the point in the interval, but if this limit exists, means that it is actually independent of the point xi I. I mean, you don't care which xi I am considering in the interval what is called xi minus 1 to xi. So whenever the limits of, suppose if my function is continuous functions, then this limit is always exist, and one can prove that whatever xi I can take inside the interval xi minus 1 to xi, the value will be same. Similarly here, I will have a functions f, I will have a functions of bounded variation, I will have a partitions, then I am having a Riemann Stietjes sum, and then I am saying that if there exists a number such that if limit norm of the partition goes to 0, this limit exists independent of the choice of my points, interim points Ti lies in the interval xi minus 1 to xi, then I will say that then my function is Riemann Stietjes integrable. And what is the value of this I, or what I will write I, that number I, it is nothing but a to b f d alpha. Right? I am integrating f with respect to functions of bounded variations. Okay. So this is the kind of definitions of Riemann Stietjes integral. If my functions f is a continuous functions, if alpha is a functions of bounded variation, then this limit always exists. You can prove it. This limit always exists, and it is independent of the choice of point Ti. So therefore this I is exist, and that I will say that integrations f d alpha. Like if I have a continuous functions defined on a closed interval a b, then my function is always Riemann integrable. That means this integrations a to b fx dx always exist. Same way, if my functions is continuous and if alpha is a function of bounded variations, then Riemann Stietjes integral of f with respect to d alpha always exist. And this is the definitions. Okay. So that is one. Now this is one theorem to tell you that yes, if my function is continuous, in fact that is the kind of, you can state it as a theorem, as I said. So earlier one is the definitions. So now this is the theorem that limit of norm of the partition goes to 0 of the Riemann Stietjes sum always exists. This is the theorem. I am not going to give the proof of it, but one can prove it is a kind of very standard theorem, and the proof you will get it in many standard books. For example, if you like, so this book like Conway. So if you look at Conway book, so these are the things are available. In fact, like functions of bounded variations, and then Riemann Stietjes, the notions of Riemann Stietjes integral, and then the contour integration. So whatever the definitions I am giving here, you just follow one book. That is, I am following actually Conway book, Conway complex analysis. You just go through that book. Well, so this, I think that proof is there in that book, but I am not going to discuss here. What is that? So let gamma be a functions of bounded variations. I have already discussed. Suppose that your functions f is continuous functions, then look what I am saying, that then there exists a number I, such that for any epsilon there exists a delta such that whenever if I take partitions P with norm of the partition is less than delta, then the corresponding Riemann Stietjes sum, the difference between the number I and the Riemann Stietjes sum will be less than epsilon. So that is nothing but limit norm of P goes to 0. If I say that this is my SPF alpha, SPF alpha, that is exactly equal to my number I. So that is the thing now. So distance between this minus this I can make very small whenever norm P is less than delta. So therefore if my functions f is continuous, in alpha is a functions of bounded variations, then I will always have the existence of I such that the distance between I and the Riemann Stietjes sum I can make less than epsilon if norm of P goes to 0. That means there should exist a delta such that whenever norm of P, that means norm of the partition, is less than delta, then the difference between my Riemann Stieltjes sum and that number I is less than epsilon. So that means this I is always exist. And of course it is whatever the choice of my point Ti inside the interval xi minus 1 to xi. So you can have it, you can take it as a theorem, you can prove it. In fact, one can prove that if my functions is continuous, if gamma is a function of bounded variation, then this limit always exists. So therefore my function is Riemann Stieltjes integrable with respect to a functions of bounded variations gamma. Okay. This is another connections with the Riemann integrations. What is that? It says that now if gamma is a piecewise smooth, now if you recall in my last lecture when I was talking about functions of bounded variation, then I say that if my gamma is a piecewise smooth or contour, then it is a function of bounded variation, right? Now if I have a piecewise smooth function, that means it is a function of bounded variation, and if I have a continuous functions, then I can have the notions of what is called Riemann Stieltjes integral. That means integrations of f with respect to a functions of bounded variation f d gamma in this way. And one can prove that that is exactly same as these Riemann integrations. So this is nothing but integrations a to b f t gamma prime t dt. Okay. So now what that means? What that means? You can say that this is integrations a to b gt dt. What is my g function? G functions is f t gamma prime t dt. F t gamma prime t. F is continuous. Now gamma is piecewise smooth. That means gamma is differentiable, not on whole but except finitely many points. Gamma prime is continuous. So therefore this function is actually not continuous on the full interval AB, but it is continuous all point in the interval AB except finitely many. But there you can make sense of these Riemann integrations of this kind of functions, integrations a to b fx dx. Of course, if my function is continuous, then it is integrable. Even if my function is not continuous on the full interval, suppose it have finitely many discontinuities, but still I can make sense of my Riemann integrations in the real analysis, you know. So this is the connections between the Riemann Stieltjes integral and the Riemann integrations you are familiar with in your real analysis. So therefore, if my functions gamma, which is piecewise smooth, that means it is a function of bounded variations, and if I start with a continuous functions f, then the corresponding Riemann Stieltjes integral, that means the integrations of f with respect to a functions of bounded variation, it's exactly equal to the corresponding Riemann integrations where your integrand is ft times gamma prime t. So that means what? That means there is a connection. That means, so just whatever knowledge you are kind of concept you are familiar with the Riemann integration, using those concepts, and now I am defining what is called Riemann Stieltjes integral. So therefore you do not worry or do not kind of get scared what is Riemann Stieltjes integral. Actually for the computation purpose, if I have a piecewise smooth curve, that you can calculate your Riemann Stieltjes integral in terms of Riemann integrations, and that you know how to calculate it. Okay. So now I think I have like all the machineries I have. Now I am in a position to talk about what is called line integral or contour integrations. Yes. So this is the definitions. So this is one of the fundamental kind of concepts in complex analysis. It says that, look, suppose z is equal to gamma t represents a contour. So that means contour means it is a piecewise smooth curve. Since it is a curve, it will have a parameterization. So suppose z is equal to gamma of t, which is a parameterization which represents a contour of piecewise smooth curve. What is my curve? I am saying that this is my curve is C. So that means you can say that C is nothing but gamma t, which is same as Z, whatever it is. Okay. So this is my parameterizations. So suppose C is a piecewise smooth curve or it's a contour. Suppose it will have a parameterization, say gamma. Okay. Now what is the initial point? So initial point is gamma of A, which I denote it as Z1, and gamma of B, which is the end point. That means I am saying this is Z2. So that means I will have a piecewise smooth curve starting from the point ZA to ZB, okay, piecewise smooth. And suppose you have a functions f defined on the contour. Suppose if this is my contour C, suppose I have functions defined on C. Now we can define the line integral or contour integral of f along the curve C, okay, and that I denote it as integration over C fj dz, okay. What is that? It says that, well, this is nothing but like the Riemann Stieltjes integral. That means I am integrating a functions with respect to a functions of bounded variations. Now what is my functions this time? So this is, you can say that this is actually integrations a to b gt d gamma t. That means this is nothing but the Riemann Stieltjes integral. So what is my gt? My gt is nothing but f of gamma t. So this is the corresponding my complex valued functions. So if I have a contour C, it will have a parameterization as gamma. Then you have a given functions f defined on the contour C. So therefore f compose gamma makes sense, right? So let it be g functions. So g is a complex valued functions defined on the closed interval AB. Gamma is a piecewise smooth curve or piecewise or contour. So it is a functions from closed interval a, b to c, but piecewise smooth curve or contour is a functions of bounded variations. Then I am saying that you just define integration c f z dz is nothing but the Riemann Stietjes integral of f with respect to gamma or integral of f with respect to a functions of bounded variation gamma. But I know that that I can calculate in terms of Riemann integrations since gamma is smooth. So therefore this is nothing but integrations a to b f of gamma t gamma prime t dt. So this is my definitions. So therefore if I have a smooth contour, so suppose this is my piecewise smooth contour C. If I have a functions f defined on my piecewise smooth contour C to the complex plane C, then what is the meaning of integrations or contour integrations or line integral of my functions f on C, which is nothing but what we have to do. Since C is piecewise smooth contour, it will have a parameterization, say let it be gamma. Then what you do, you consider these functions f composition gamma. Okay, this is a map from closed interval AB to C. Okay, that is one functions. And if gamma is piecewise smooth, that means gamma is nice, your f is nice, that means this function is a nice functions from closed interval AB to C. Since gamma is the parameterizations of a piecewise smooth curve, it's a function of bounded variation, then I am saying that consider this Riemann Stietjes integral of f compose gamma with respect to a functions of bounded variation gamma. So these integrations I am saying that this is same as I am defining it. The integrations of f compose gamma with respect to a functions of bounded variation gamma is nothing but the definitions of contour integrations of f over the contour C. So integration C f z dz, which is nothing but the corresponding Riemann Stietjes integral f of gamma t d gamma t, which in my last slide I discussed that if my gamma is piecewise smooth or contour, so therefore that Riemann Stietjes integral is exactly equal to the corresponding Riemann integration. That means this is same as integrations a to b f of gamma t gamma prime t dt. So therefore now if I give some kind of problem, okay, calculate the contour integration. Suppose this is your contour, then what you have to do? First, if I give a contour, first you have to find what will be the corresponding parameterizations, right? That is very important. First you get the parameterizations, then you just calculate these integrations because your f is known. If you know your parameterization, that means f compose gamma, that function is known, you know gamma, then you just calculate this corresponding Riemann integrations. If I calculate this integration, it will give you the value of my line integral or contour integral of f over the contour C. Okay, look. So I'm saying that one more kind of comment. If fz is, I do not need continuity on the full interval. Even my function is piecewise continuous on the contour C. That means it is not continuous on the full contour, but again, if it is continuous, piecewise continuous, that means what? That means I can chop my contour C into finitely many pieces. So except finitely many points on my contour, my function is continuous. Even then, the above integral exists. That means I can make sense of this kind of integrations, or I can make sense of this Riemann Stietjes integral, and then I am saying that this I denote it as what is called contour integral of f over my contour C. So what is my contour integrations? If I just kind of combine everything, so start with a contour of piecewise smooth curve, then you will have a parameterizations, right? Start with the functions defined on the contour. Take my function is continuous or piecewise continuous, then I can define the contour integrations of f over the contour C. I will denote it as this object integrations over C f z dz, which I define as the Riemann Stietjes integral of the functions f compose gamma with respect to a functions of bounded variation gamma, then where gamma is the parameterizations, and f compose gamma makes sense because f is defined on the contour and gamma is the parameterizations, which is same as the Riemann integrations a to b f of gamma t gamma prime t dt. Now if my f is piecewise smooth, gamma is parameterizations of a what is called contour, then f compose gamma t times gamma prime t, this is a map g t goes to this map, t goes to f of gamma t times gamma prime of t. This is also, you can have a piecewise, this function is also piecewise continuous, so therefore the corresponding Riemann integration exists, and you can easily calculate the Riemann integrations if you know the parameterizations of your contour and the functions f. So therefore this is the definitions of what is called line integral or contour integral. So one example you can easily calculate it. Okay, so what is that? So okay, compute that integration c z bar. So what is your functions f of z, which is z bar, right? And what is your contour? Contour, okay, this time I have given the parameterization c, which is zt 2 times e to the it, where t runs from minus pi by 2 to pi by 2. Then you can easily calculate it. By definitions, this is the definitions. What is the definition? Go back, come back here. So this is, you know contour c, you know your function. So what is that? So therefore this is exactly from a to b. A to b means what? It is the parameterizations, is the left hand point a, right hand point b. So what is the parameterization? T runs from minus pi by 2 pi by 2. So therefore minus pi by 2 to pi by 2. Then what is f of gamma t? What is your functions f here? F of z is equal to z bar. And what is your gamma? Gamma of or zt, whatever gamma t, which is 2 times e to the power it. So f of gamma t means what? So that means f of gamma t, which is that, then 2 e to the power it whole bar. So that is the 2 e to the it whole bar. Then gamma prime t, you know what is gamma prime t? Gamma prime t is 2 times I times e to the it. So therefore 2 times I times e to the it, and then dt. You just calculate. Now you are in a situation to calculate Riemann integrations. You can do that. What is that? So this time what will have? 2 times e to the minus it, this. So it will have this one, and this is this one. But only difference is that this time, though I am saying that it is Riemann integration, but you have to be little bit careful, because this function t goes to f of gamma t times gamma prime t, this is no more a real valued functions, it is actually complex valued functions. So therefore you are actually integrating a to b gt dt, where g is a complex valued functions. But I already discussed in my earlier lectures that if I have a functions g which is taking complex valued from the interval a to b, then you can write g is of the form u plus iv, and then I am saying that integrations a to b g, which is nothing but integrations a to b u plus I times integrations a to b v, and that you know. Okay, so that Riemann integrations you know. So therefore now the way I have given the definitions, one example you can easily calculate it, and it turns out that the corresponding what is called line integral is value is nothing but the 4 pi I. Okay, so there are many problems, you can have it in many books there, where you can just take functions, take a contour, and just try to calculate using this formula, using the definitions of what is called line integral and contour integrations. Now couple of properties like the Riemann integrations or Riemann Stietjes integral, the properties are there. Same thing, it's true if alpha and beta are complex number, if f and g are piecewise continuous complex valued functions defined on my contour c, then integrations c alpha f plus beta g is nothing but alpha times integration c f dz plus beta times integration c g of z dz. That means linearity property. That means you can take out your scalar outside of the integrations. Like Riemann integration and Riemann Stietjes integral, this is true. Like in the Riemann integration, I should say, because if you are not comfortable with Riemann Stietjes integrations, okay, this is one. So this is also true. Like for example, if I know for Riemann integrations a to b fx dx, which is, and if I take some point say c in between, say this is my a to b. If I take in between point c, then these integrations one can calculate a to c fx dx plus c to b fx dx. So same object. So if I take an interval ab, if I take any point c in between, then integrations a to b I can break up into two parts, a to c and c to b. Same thing here. If I take a contour c consisting of contour c1 from z0 to z1 followed by a contour c2 from z1 to z2, that means you have point, I have written, okay, this is my picture. So this is z0, this is z1, this is z2. So I have a contour c1 from z0 to z1, I have a contour c2 from z1 to z2, and I am saying that c is equal to c1 union c2, total contour. Then one can say that this contour integrations or line integrations over C I can break up into two parts, contour integrations over C1 and contour integration over C2. Because if I give some kind of contour total, so that means the point is that if I give a some functions a which is a nice, and if I give some contour and I am saying that calculate the contour integrations, what you have to do? First part you have to get the parameterizations of your contour. Now if your contour is very complicated, or that means to get the parameterizations is complicated, that means the of course line integral and contour integral will be difficult. Now if I give some contour, and if you see that I can break that contour into finitely many pieces, and each piece I can easily have the parameterizations. So using these properties you can break your contour integral into finitely many contour integrations, and each of the contour you know what is the parameterizations, or you can calculate the corresponding contour integrations or line integration. That is why it is very useful. For example, this is the total contour C, but this is a straight line and this is some kind of nice curve, say either part of the circle. That means you know parameterizations of this C1 and parameterization of C2. So therefore you can easily calculate this contour integration and this contour integration. So if I sum it up, you will have the contour integrations over C, even though you do not know the full parameterizations of C. Okay, so this is one of the nice properties to evaluate what is called line integrations and contour integrations. Okay, another two properties. So it says that if I have a continuous piecewise complex valued functions on a contour C, and given a contour C, I have defined what is minus of C, like negative of that curve. Okay, so like for example, integrations a to b fx dx, just always compare with the what is called Riemann integrations. Now if I change ab to ba, then there will be a sign change. That means this is same as b to a fx dx, right? That kind of formula you know. But this is an interval. Now I have a contour C, so suppose this is my contour C starting from say some point ZA to say ZB, and suppose this is my I have a parameterization, so the natural orientation is there. Now if I have a C, so then what is my minus C? It is the same set of points, but this time I am going from ZB to ZA. So this is the orientations of minus C. So now the question is, I have defined integration C fz dz. What is, and also minus C is another contour, right? Minus C fz dz. Is there any relations? Answer is yes. Like from a to b fx dx is same as minus of b to a. Similarly here integrations over minus C fz dz, which is same as minus 1, will come out integration C fz dz. Same properties. So like you know, in the case of Riemann integration, that is also true for what is called contour integrations. So okay, so integrations over the negative of the curve, opposite of the curve, is same as minus 1 will come out, then integrations over the contour C. So that is one properties, and I'm not going to anyhow this kind of formula you can easily prove it, okay, because you know the parameterization. If you know, suppose C has a parameterization is gamma, then you know the parameterizations of minus C. What you can do, you just write what is the definitions of line integral or contour integral in terms of Riemann integrations, then use this formula, you will be able to prove this formula. I'm not going to prove it, okay, I'm just giving the hint. This is very much useful, number 4. This is called ML inequality. What is that? It says that if my function is piecewise continuous or continuous functions, complex valued functions over the contour C, which has a parameterization z of t, then I can estimate. For example, if you remember, if I have a complex valued functions a to b to c, then I can estimate, na? So gt dt, this is lesser equal to integrations a to b mod gt dt, right? So that means I can push the modulus inside the integrand, but there will be a lesser equal to sign. Similarly, I can estimate my what is called contour integrations, and in what term I can estimate? It says that it is m and l. What is m and l? M is the upper bound of my absolute of my functions, value of the functions where z lies on the contour. So suppose this is my contour C. Since my functions defined on C, so if I take any point z is in C, so what you do, f of z absolute, and take the what is called supremum of f of z where z lies in C. So that is, I am saying that this m. And what is my L? L is the length of my curve. So in terms, so what is the upper bound? So that means I can estimate my contour integrations, which is dominated by m times L. What is my m? M is the absolute of the values of my functions over the contour and taking the supremum. That means this is the upper bound. And what is my L? L is the length of the contour. Okay, so m is the upper bound of this kind of set. Of this set, absolute of f of z, z lies in C, and L is the length of the contour. Well, one can say that when the upper bound will exist. Now, if my function is nice, continuous functions, and since it is a contour, that means it is a, later on you can, I will explain. C is a contour means it is a compact set, so therefore continuous functions on a compact set, it will have the supremum will exist, so therefore supremum of this object will always exist, okay. As a continuous image of a compact set is compact, so that's what the fact I am using here, okay. But the most important part is that this line integral or contour integral, you will have the estimate which is lesser equal to m times L. You can prove it. Look, so what is this? This is integration C fz dz, okay, and so you can say that this is always lesser equal to integration C modulus of fz times dz, and this is same as well. In fact, you can easily prove it. So what is that? Integration C fz dz, if you remember, by the definitions of contour integrations, since this is a parameterizations, so this is nothing but a to b f of zt, then z prime t dt, right? So now I can estimate it. But now you know this kind of formula. If I have a complex valued functions defined on closed interval ab, then I have the estimate absolute of this. I can push the modulus inside the integrand, and there will be a lesser equal to sign. So therefore this is lesser equal to integrations a to b absolute of f of zt times z prime t dt, right? So that's what I exactly have written, right? But now what is that? F of zt. Now if t runs from a to b, zt runs over the contour c. So this is nothing but absolute of f of z, z lies on c, and suppose this is my supremum m. So therefore this integrand, so I can say that f of z of t, which is dominated by m for all t inside ab. So therefore this I can say that you can have it, for example, you can say that. So this is lesser equal to because of this fact I can say that this is lesser equal to m times a to b z prime t dt. But if you remember when I was talking about what is called differentiable curve in my earlier lectures, then how to calculate the length of the curve. Now if your curve is differentiable curve and suppose z is the parameterizations, right, then length of the curve is nothing but this is the formula, right? So integrations a to b absolute of z prime t dt if z is the parameterization. So therefore this is exactly equal to m times l. Sometimes this is called ml formula. So therefore if I have a functions, nice functions, if I have a what is called contour C, then I can estimate my contour integrations or line integrals which is dominated by m times l. What is l? L is the length of the curve, and what is my m? M is the supremum of absolute of f of z, or z running over my contour C. Okay, so this is one kind of using ML inequality you can easily prove that. So if C has a parameterizations, if your function is this, then by ML inequality you can easily prove it. And it's also true. Why? You just look at the definitions. What is the definition? Because this is my parameterization is given. So therefore this should be 0 to pi by 2 f of gamma t, then gamma prime t dt, right? So this is what? And this is dominated by what? M times L, right? What is m? M is the supremum and L is the length. First of all, what is the length of the curve? So what is this curve? So if I take, this is circle, right? But this time I am, it's a circle. If t runs from 0 to 2 pi, it will give you a full circle, right? With radius 2. Now I am going from 0 to 2 pi. That means I am just only considering this part, okay? So what is the length of this part? So the total length is what? 2 pi, and I am just 1/4 of that. So that means this is actually what? Yeah, so this is actually, sorry, total length is, so circle of radius 2, so total length is 4 pi, right? So 2 pi r, 2 pi times r means radius, so that means this should be 4 pi, right? So I am considering only the first quadrant, so that means the length is pi. Okay, so m is, so L is pi, so that is given. What is my m? M is the supremum of f of z, where z running over only the first quadrant, right? So that means z running over, or you can say that, yeah, so z running over this portion, right? This portion, part of the circle, right? But you can easily calculate. So what is f of z? So z means, you can say that this is also supremum of f of gamma of t, because parameterization is given. And what is t? T runs from 0 to pi by 2, right? So I have to calculate this supremum. But f is given. So what is f of gamma t? We just calculate it. So this should be what? This should be, well, I do not need it, maybe just, okay, fine, okay. So this should be gamma of t plus 4 divided by, gamma of t q minus 1. Well, I'll have to estimate it. So there are many ways you can do that, okay. One of the way is the following, I'm doing it, okay. I'm just doing it, okay. So look, so what is f of z? So f of z absolute, which is same as z plus 4 divided by zq minus 1, right? Now I will use one inequality. What is that? If you remember, I have proved in my earlier lectures, absolute of A minus B, which is greater or equal to absolute of mod A minus mod B. I will use that fact. So if I use that fact, then you can calculate this one. So ZQ minus 1, which is greater or equal to modulus of mod ZQ minus 1. Right? But what is mod Z? Mod Z, Z is running over the contour. That means mod Z. What is the mod Z? Mod Z is always 2. So therefore you can say that this is 2 to the power Q minus 1. That means this should be 7. Right? Because mod Z, Z is lying over the circle of radius 2. So therefore mod Z is 2. So therefore this denominator is always greater or equal to 7. So therefore this is lesser or equal to mod Z plus 4 divided by 7. But this is same as by triangle inequality, mod Z plus 4 divided by 7. But what is mod Z? Again, Z running over the circle. So therefore this should be 2 plus 4 by 7. That means this should be 6 by 7. So therefore absolute of f of z, where z running over my contour, this is portion of the contour, this is the contour actually, portion of the circle. So that means absolute of mod of f of z, or z running over this, which is dominated by 6 by 7. That means this is my m, right? Dominated by, I am saying. And L is pi, so therefore this is dominated by 6 by 7 times pi. Okay. So since f of z, z running over this one, so therefore you can easily say that supremum of f of z, where z running over your contour, say C, which is dominated by my 6 by 7. So therefore this m, which is lesser equal to 6 by 7. But I know this object which is always dominated by m times L. Now m is lesser equal to 6 by 7, L is exactly equal to pi. So therefore this is 6 by 7 times pi. So this kind of problem you can calculate it, okay. Just use the what is called definitions of contour integrations and you can have it. Okay. So now this is what is called fundamental integral, that you can easily calculate it. So I am not just giving a hint. Okay, you can easily calculate it. For example, if I take n is equal to minus 1, so the say n is equal to minus 1, then this is becomes integration CAR 1 by z minus a dz, right? And CAR, what is CAR? CAR denotes the circle of radius at centered A. So therefore, so suppose this is my A and this is circle of radius r. So therefore what is the parameterization? So just only thing you need to check, what is the parameterizations. CAR will have a parameterization, let it be gamma t, and how it looks like, this should be a plus r e to the I theta or it, where t runs from 0 to 2 pi. That is the parameterization, CAR. So I am just perturbating A because A is the center. So A plus R e to the IT, because if I just take R e to the IT, that means I am talking about center at 0. Since it will have a center A, so that means A plus R e to the IT, and T runs from the 0 to 2 pi, it will be a circle. So now you will have the parameterizations, right? So gamma of T is equal to A plus R e to the IT. Now you can easily calculate this object. For example, if I take n is equal to minus 1, it will have this one, and if I take n not equal to minus 1, then what will have? You have CAR, so z minus a to the power n dz, right? What is the definition? By using the definitions of what is called line integral, this should be 0 to 2 pi. So f of gamma t, right? So that means this should be gamma t is this one. That means this should be r e to the it to the power n, right? Because what is your f functions? F of z, which is z minus a to the power n, right? So therefore f of gamma t, which is gamma t minus a to the power n. Now what is gamma t? A plus r e to the it, so therefore r e to the it to the power n. So this is okay. Then you'll have gamma prime t. Gamma prime t means what? R I e to the it dt. So you'll have this kind of definitions. So that means, in other words, the integrations will have 0 to 2 pi, r to the power n plus 1, then I will be there, e to the power I times n plus 1 t dt. So that kind of integrations we will end up with. Now you will see, if n is equal to minus 1, so it will not contribute, it will be 1, right? So that means it will have some value, and this will be exactly equal to 2 pi I, you will check it, okay? But now what will happen? Okay, so now look, so if, and that is very nice, if n is not equal to minus 1, that means n plus 1 is non-zero, right? If n plus 1 is non-zero, now come back to these integrations. Now if n plus 1 is non-zero, that means this factor will always exist in the integrand. Now this is the exponential functions, e to the power I some integer times t, and I am integrating with respect to full 0 to 2 pi, so that means its value always give you 0. So only the factor is that n is equal to minus 1, so there will be something, and if you calculate explicitly of this object, it will give you 2 pi I. Okay, maybe in my next lecture I will kind of calculate explicitly what is the value. Okay, then you will have, then I will talk about what is called path integrations and so on and so forth, and then I think what we will have what is called Cauchy-Goussard theorem. Maybe I think I should at least for this week of lectures, so I think I should stop here. In my next week I will start with what is called path independence and one of the fundamental theorem what is called Cauchy-Goussard theorem. I think I should stop here. So what I have discussed till now is that I have talked about, or I have discussed what is the meaning of contour, right? And then I give a meaning of what is called contour integrations or line integral. Okay. Now once I have a contour integration, then you will see there are many things you can have it, right? For example, just give a idea that if I take 2 points Z1 and Z2, so therefore if I take a contour here, then I can suppose this is my C1. Okay, then I can have the meaning of contour integrations of some nice functions defined on this one. Now if I take another contour here, say C2, then I can have another contour integration. So therefore it is starting from Z1 ending in Z2. So therefore one can ask, so fix 2 points in the complex plane, you have infinitely many contours starting from Z1 ending at Z2. And suppose you have a function dependent on the whole complex plane. Now you have the meaning of contour integrations. So then my question is, will the contour integrations depend on the contour? That means if I have a point Z1, point Z2, if I take one contour, it will have some value. If I take another contour starting from the same point Z1 ending at Z2, we will have the different value or we will have the same value. So that will lead you to conclude or to talk about path independency. Okay, so then you will see there are nice situations will come while you will have both path dependency and path independency. Okay, and that will lead you one of the nice theorem, one of the fundamental theorem in complex analysis, that is called Cauchy-Goussard theorem. So those kind of concept I will talk about in my next week lecture. I think for this week you just have the notions of what is called contour integration or line integrations, and I have calculated, or I have discussed couple of properties and calculated few examples that how to calculate contour integrations if your contour is given and your function is given. In my next lecture, that means in my next week lecture, I'll start with what is called path. Like I'll just explain that you cannot have that. If I have 2 points, if I take any contour joining Z1 or joining ending Z2, that path, if I take different contour, the value will be different depending on what kind of functions I am taking, what kind of domain of the functions I am taking. So those kind of things will come, and at the end we will have very nice theorem what is called Cauchy-Goussard theorem. I think next week I will talk all those things. I think I should stop here. Thank you.